So based on the prime factorization of each number, we have seen how to compute the GCD and the LCM. And based on that factorization, we have also seen the relationship between the product of the two numbers and the product of the GCD and the LCM. But you see, integer factorization, which is determining the prime factors in general of a number, is a difficult problem in the sense that we do not really have a polynomial time algorithm. Therefore, this is not really the preferred method. Okay, so especially for large numbers, determining the prime factors is difficult. It takes a lot of time. Therefore, in the general sense, to compute the GCD, computing the prime factorization is not the way to go. Fortunately, we have what we call Euclid's algorithm for computing the GCD, which is quite simple and very efficient. And of course, when you compute the GCD, you can obviously compute the LCM by dividing the GCD, or rather by dividing the product of A and B to their GCD. Therefore, this you can see as also an algorithm for the LCM. And this is based on a lemma here. Let the number A be equal to B times Q plus R, where the numbers A, B, Q, and R are all integers. In this case, the GCD of A and B and the GCD of B and R are equal. Okay, so we are after the GCD of A and B. And if you can find an expression in this form, A equals BQ plus R, which is simply the same formulation with division. Well, R here is not restricted, as you see, but obviously we can use division to obtain such an expression. And the GCD between A and B is going to be exactly equal to the GCD between B and R. So rather than computing the GCD of A and B, you can compute the GCD of B and R. And if you use division to obtain this formulation, B and R, or rather R itself, is definitely going to be smaller than A. So at every iteration, the numbers you have to work with get smaller and smaller, and therefore at some point it will be easy to obtain their GCD. Now, first of all, let's see why the lemma is true. Suppose we have a number D that divides A and B. So D is one of the common factors of A and B. So in fact, the GCD is going to be the greatest such number. But D here represents a generic common factor of A and B. Then D must be also a divisor of R, because when you have this expression, A equals BQ plus R, you can write R as A minus B times Q. But you see, D is a factor of A, and it's also a factor of B. Therefore, D is a factor of A and B times Q. So when you subtract them from each other, you still get a number that's a multiple of D. Therefore, D divides R. Again, when you look at this, D divides B and D divides R for such numbers. I mean, so D here is now going to represent the common factors of B and R. In this case, again, D should be a factor of A, since I can write A as BQ plus R. But we have assumed that D is a factor of B, so this part here is a multiple of D. And also we assumed that D is a factor of R, so this here is a multiple of D. Therefore, this sum, which is equal to A, must be a factor of or a multiple of D. Therefore, we have established that the pair A and B and the pair B and R must have the same set of common divisors. Because when you assume D is a common divisor of A and B, then it should be divisible by, so it should be a divisor of R. At the same time, if D is a common factor of B and R, we establish that it must also be a factor of A. Therefore, AB and BR have the exact same set of common divisors. Therefore, the maximum of that set, which is the GCD, must be the same. Okay? Simple as that. Then the algorithm, Euclid's algorithm to compute the GCD is based on this simple observation. And it's given here. I don't need to go line by line. If you want, you can go iterate this on some examples. But essentially, what you do is when you are given the pair A and B, you compute Q and R. Well, you don't need Q, you just need R. Therefore, to compute the GCD of A and B, rather you compute the GCD of B and R. And to compute the GCD of B and R, you apply the same principle. You divide B by R, you find the remainder, let's call it R1, and then instead of computing the GCD of B and R, you compute the GCD of R and R1. And you do this until you reach one of the divisors become 1. Okay, therefore, in this case, the GCD is going to become obvious. Therefore, here, let's see this on an example. Let's compute the greatest common divisor of 287 and 91. Well, in terms of computation, these numbers are quite small. So if you give them to a computer, even if you just perform a search, a brute force method, it's not that difficult to find the prime factors and the GCD of these two numbers. But this is just a demonstration, and just consider this working on huge numbers. So to compute the GCD of 287 and 91, what you do is you divide 287 by 91. So you get 287 equals 91 times 3 plus 14. So you put this number in this form using division. Okay, I don't care about this. At this point, I just need the remainder. Okay, therefore, the GCD of 287 and 95 must be equal to the GCD of 19 and 14. So, sorry, 91 and 14. You see, the problem has gotten easier because instead of 287, I now get to work with 14. And therefore, now I need to find the GCD of 14 and 91. Since 91 is the greater, I prefer dividing 91 by 14 and write 91 equals 14 times 6 plus the remainder 7. Okay, now instead of the pair 14 and 91, I'm going to find the GCD of the pair 14 and 7 because I know that they are going to be equal. Now, at this point, it should be obvious to you that the GCD must be 7 because it's clear from the two numbers. But if you actually follow the algorithm, it's looking for one of the numbers to reach 0 so that the remainder is going to be 0. And therefore, you continue the procedure and write 14 as 7 times 2 plus 0, where you have the remainder as 0, which will terminate the algorithm. And therefore, this is going to be the GCD. Okay, 7 is returned as the GCD of the numbers 287 and 91. And you see, we did not really need to factor out these numbers into their prime factors.